Okay, so I think last class we were talking about DN groups. It started with the DN. DN means it will have CN and then n times of C2 axis perpendicular to CN. So that is the primary requirement. That should be n times of C2 axis of symmetry, which is perpendicular to the CN symmetry. Examples I was listing what for D2. Okay, I didn't mention it, but it is for D2. It is copper, ethylene diamine twice 2 plus, and then so you got it. I think I asked for which one is possible. Anyone tried? I think one person replied. Anybody else tried? Copper. I mean, this is this ethylene diamine copper 2 plus, right? So this will be say just point it out. Something like this will be there. So N will be here. Okay, so this is a copper, and then 4 N's will be there. And these are CH2 groups, CH2, 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 CH2. This is N with certain balance. So this molecule has D2 point group. So you can say this is copper, okay? So this is Cu. So here you can see this is that means it has C2 and 2 times of C2 perpendicular to again C2. So principal axis is C2. So if you put the line, dotted line means I just consider this is going through this board, passing through this copper, C2. Okay, so and there are 2 C2s which are perpendicular to this C2. Okay, so one is this one through this plane, and another one could be bisecting these two molecules into two, which is on the plane. Yeah. So those two are these two C2s perpendicular to the axis of symmetry, the C2 axis of symmetry. So this is D2 point group. We'll take one more example for. I think I gave it for D3 also. So let's talk about D3. Its example is cobalt again. Ethylene diamine tris. So I think this is 3 plus. So anyone tried? What is the structure of this? Looks like it is tris ethylene diamine cobalt 3 plus complex. I can draw. Let me draw. So this is from this point. So there is a cobalt here. It will be something like this. So this is all N. I'm not fitting the valency, but still just consider as N. Okay. So this molecule is what? So this is this ethylene diamine. Okay, so this is basically this ethylene diamine. Okay, this is tris ethylene diamine cobalt 3 plus complex. So that's why you have 3 ethylene diamines. And then this forms a C3 point, a D3 point group. So it is not in the planar. If you see these two will be in one axis, then this group will be in out of the plane. So this is cobalt here, and then so if you consider C3 axis, so it has C3, okay, which is principal axis. So this will be going through this board, that is C3. So I can write here dotted line, which shows this is C3, and then it has 3 times of C2 perpendicular to C3. Okay, so 3 C2 axis will be there. So shall we write where the C2 axis are? So I just, it's C2 axis is perpendicular to the C3. So C3 we consider perpendicular to, across the board, and then C2 you can consider passing on this side of this. Which is cutting the molecule into 2. So that is 1 C2. Similarly, you can have one more here. Okay, and then this is again, you can cut the molecule off through this ethylene. So there are 3 C2s perpendicular to the C3 axis, which is principal axis.
Excuse me, sir.
Yes.
Sir, is it planar or propeller shaped?
No, it is not a planar. It's not possible to have a planar molecule. You simply in Google, I think you can just type this molecule tris ethylene diamine cobalt 3+. You just type that, and then you will get the structure. So it's a 3-dimensional. It's like it's like what? It cannot be planar. Just
Propeller, sir.
it's not planar, basically. Yeah, so one has to come out of the board. Yeah, so it will be something like that. But you can view the image will be 3-dimensional view will be very nice. Just take a look. Okay, so this is about D3, and D5 is example is twisted ferrocene. So that is a D5. Okay, so D5 is twisted ferrocene. I can draw, but I suggest you better view it yourself. Basically, 2 cyclopentyl group overlap, but just twisted a little bit by a certain angle. So I just start from here, then go here, and go here. So, 1, 2, 3. Has to go here, and then join here. So you will have a twisted ferrocene as D5. So there is a ion group in between, and then of course there are 2 circles. So twisted ferrocene is ferrocene twisted. Ferrocene, is it twisted or staggered? Let me check.
It's twisted, sir.
Which one? Twisted. D5 is yeah, twisted. Twisted is fine. So ferrocene twisted. Or some books, right, they say staggered also. But anyway, so just simple 2 cyclopentyl groups.
Sir?
Ah.
Sir, I don't think that twisted ferrocene is D5. It's D5D. It has sigma D planes also.
No, staggered is D5D.
So staggered is same as twisted, right? What is the difference one?
Yeah, staggered is much. Let me. Yeah, some books say this one. Twisted is. Let me check. I agree. Staggered has sigma D. Okay. What is twisted? Twisted is which is not having sigma D plane. So it is twisted. What I mean is it is not exactly symmetric. So it is not the second ring cyclopentyl group is not exactly symmetric, but it will be just tilted by certain angle, but not exactly splitting into half. So that is called as twisted. That is also called as ferrocene staggered. So that is basically D5D. But twisted is generally D5 only. I mean, there are different ferrocene. The ferrocene you have to take three. One is Eclipse, that is very well known, and D5D is the ferrocene staggered, which just symmetrically splits. I mean, symmetrically shifted, like in staggered conformation of C2H6. That is a perfect shift. No, everywhere, every angle was same. Every angle is same, shifted. That is same way in ferrocene also. Every angle, I mean every carbon is shifted by 30 degrees or so. Okay, so that is staggered. Twisted means it's not exactly at the off distance, off angle. It may be close to this. We are not drawing exactly. So say it starts from here, it goes here, and then goes here, and what? Long one. It goes here and then comes in. Okay, a slight shift. It's not exactly at the center, the second ring, but slight. I mean, if you have two rings, eclipse, I mean the ferrocene eclipse, slight shift. So that is called as twisted. Okay, so there are three point groups for ferrocene. One is for eclipse, one is for staggered, and one is for the twisted. So here D5 is for the twisted. Okay, you read the books, no? Read the books, or in the there are good websites for group theory. You just see the example, and you just Google it, ferrocene twisted structure. It will show how it is. It's not exactly symmetric, so it doesn't have sigma D planes, because sigma D plane it has to pass through center, right? So when you do that, it won't pass through the center. I mean, these are all located at the same position, so then it will not have sigma D, the twisted one. Let's since you're talking about the ferrocene, let's start with D and D point groups. So in D and D, okay, somebody asked. I mean, you agree there is a difference of twisted and staggered?
Yes, sir.
Okay, fine. Now let's come to D and D. So again, D and D, it will have a Cn, n times of C2 perpendicular to the Cn, and also it will have sigma D. Okay, so this additional plane will be there. That is D and D. It could be having sigma V's also. But if the molecule has sigma D, then it will be labeled as a D and D. Okay, so the same molecule can have sigma V's. It doesn't matter. In addition to sigma D, there can be sigma V's also, but still it will be labeled as sigma D, D and D. Okay, so that is. I'll just give you some examples. So one is okay, simpler one. Let's start. C2H6 staggered conformation. Or anyway, let's stick to this staggered conformation. So I just put Newman projection staggered, right? So I just draw this. So these are all H. Not meter, but just H. So C2H6 staggered is a DN D D to D point. So it has what C2 it has followed by 2 times of C2 perpendicular to C2. First C2 is principal axis. You can say just passing axis of principal axis is passing through
So, sir, it's D3D.
Okay, D3D, yeah, okay. Yeah, fine, fine. So it's D3D. So it should be D3 perpendicular to 3, C2 perpendicular to D3, no, C3. And what else? And then it has sigma D. Okay, everyone get this for yeah. So that should be a 120-degree rotation. If you pass through this central carbon atoms, then it will rotate 120 degrees to get the symmetrical structure. So that's why it has C3. And then what? Through this, so this is, you can say this is across the board, that is C3. And then now 3 times of one is through this axis. You can rotate it, right? Rotate the molecule like this. Flip it, just flipping it. So this hydrogen will go here, this hydrogen will come here, and whatnot. Same way, other things also change, interchange. So that is 1 C2. And all the 3 carbon atoms, you can do that. So this is second one. You can flip it. And then again through this carbon. Through this form. So you can do that. So 3 times you can do it. So that is 3 C2 perpendicular to the C3. So these are all the flipping on the plane of the board, which is perpendicular to the C3 axis. Yeah. What else? Sigma D is basically a plane which is passing through 2 sigma V planes, you can say, or which cuts the angle between 3 atoms. So basically, yeah, every C2 you have put no, so you can place a sigma D plane. So here you can put a plane here. That is sigma D. So there could be 3 sigma Ds. Okay, it's not just not 1 sigma D, but there could be 3 sigma Ds. Wherever you have put sigma 2 axis of symmetry, there everywhere you can put sigma D plane. Sigma D, and again here. So you get symmetrical structures to place it. Yeah, so this is D3D for example is staggered conformation of ethane. As we have discussed earlier, the ferrocene staggered conformation is also D5D. That is D5D. I don't want to draw it again. You practice it. I hope you practice yourself because in the exam it will be very difficult. So you just start from the central point and goes all the way here. So this is I'm drawing correctly. So it will be very highly symmetric. So this is ferrocene staggered. Okay. So this is ferrocene staggered. This is D5D. It has DC5, 5 times of C2 perpendicular to C5, and then 5 times of sigma D will be there. Yeah, so sigma D, since it has sigma D, so you can place a mirror here, place it here, place it here. It's difficult to. Every carbon atom you can place here mirror. So 1, 2, here again you can place it here, and then 4th here, 5th here. So like this you can place a 5 mirrors. So those are called as sigma D planes. Okay, so that's why it's called as D5D group. And what about there is another type of point group. It is called as DNH. So molecule can have, in addition to other symmetries, if it has sigma H, then it is called as DNH. So this point group is called as DNH because it will have sigma H. It can, the molecule, yeah, if the molecule has sigma H, then you call it as DNH along with these two conditions. And some molecules can have, in addition to sigma H, it can also have sigma V or sigma D. Okay. Some molecules can have only this much, or you can also have sigma V or sigma D. Still, if all these things are even present, you label it as D and H only, because whenever the molecule has sigma H, the preference is given for sigma H. Okay, that's why the H is given in the labeling. Okay, so I think we already saw the examples. One is D4H. Let's go with the example which we took yesterday, XCX4. XCX4. So this is D4H. Yeah. So what is having is XCX4 is planar molecule. XCF. So it has what? So C4, then 4 times of C2 perpendicular to C4. So I think you have C4 which is passing through the xenon, and then it has C2, 4 C2s through this atom, this atom, this. You have 4 C2s which are pertinent to C4, and then that could be an additional C2 also possible. If you rotate it to 180 degrees, so that C2 is different. Okay, so still that's possible. This C2 is perpendicular to the C4, and then what else? So sigma H is present. Okay, so since sigma H is present, so this point group is D4H. But not only that, it has sigma V's and sigma D. So it has everything. Sigma V's are all which are, you can cut it like this, cut it like this. So sigmas, multiple sigmas are there, and then but only one sigma H. Okay, and then you have, so sigma V's are here. Yesterday we saw it. Right? You might have noted down. So this is sigma V's, and then sigma D's, which is perpendicular to the sigma V here. So these two are sigma D's. So this molecule is having in addition to sigma H, it has sigma V and sigma D. Okay, so basically it has 2 sigma V's, 2 sigma D's, and it may ask why not I? So I is also there. Okay, and if you notice, it has C4 followed by sigma H. So there is you have both symmetries C4 and sigma H. That means it has S4. So S4 is improper rotational axis of symmetry, right? So S4 is basically combination of C4 followed by, so it is equivalent to C4 followed by sigma H, right? So that means if the molecule has C4 and sigma H, you call it as it has S4 also. So as somebody was saying, the other example is the eclipse conformation of C2H6 is D3H. Okay, so C2H6 eclipse. So again, we put that in one projection. So I put hydrogens next to it. So this conformation has this is eclipse. So this molecule is ethane eclipse D3H. Okay. so you can find out what are the symmetry elements present. So it will be having C3, and then sigma h. Where do you have sigma h? When you split, when you place a mirror, we place a mirror somewhere here. Okay, so we have that mirror. Then the sigma h mirror cutting two carbon atoms. So this is C1, this is C2. You cut the two atoms, then you will have a mirror mesh. I mean, both the Y's will overlap. So it has C3. Many things it has C3, 3 times of C2 perpendicular to C3, and then sigma h. So like that you will have, right? Okay, this is all about D NH point group. So I don't tell. I think ferrocene eclipse is D5H, and benzene. What about benzene?
D6H.
Yeah, so D6H. So that's the best example to explain D6H. So benzene is D6H. So we can write it quickly here. So this is 6. Okay, this is C6. 6 times of C2 perpendicular to C6. Yeah, so I think I can draw a dotted line, meaning a line passing through this phyllo, that is C6. And then 6 times of C2. So basically, for every carbon, you can pass through a C2 axis. This. So that could be multiple 6 C6, I mean C2. 6 C2 is possible. Similarly, sigma V is also possible, right? When you cut the molecule through this 2 carbon, so it gets into off. So there are multiple sigma V's. But main thing is sigma H. The molecule you can slice it through carbon atoms. So you can place a sigma H plane. So it just cuts into off. So sigma H is present. So since you have this condition satisfied, this condition having sigma H, that's why it's called as D6H. Yeah. And of course, it has I symmetry, and since it has C6 and sigma H, it can have S6. So other possibilities also. So that I S6. Okay. So let's stop this D6 business. DN point group. Let's go to something else. Okay. So what is C infinity B? The point group C infinity B.
Hydrogen molecule.
So it's a linear molecule C infinity B, right? So there are 2 examples. One is 2 different type of point groups. One is C infinity B. There is D infinity H. Okay. So D infinity H is carbon dioxide is a good example. And any other example for D infinity H? So basically, D infinity H means it has infinite times of C2. Yeah, so you can rotate multiple times. Huh? So that's why it's called as D infinity, and along with that, it has sigma H. Yeah, so basically C infinity it has, and then infinite times of C2, and then sigma H. So that's why it is called as D infinity H. So linear molecules, all linear molecules, you can rotate in various angles, right? I think so that's why it is coming infinite. So infinite time of C2 is possible. So because you can rotate at various orientation, so that's why it is C2, which is perpendicular to C infinity, and then sigma H. You can have sigma H also. So any other example?
C2H2.
Huh?
C2H2.
C? I'm not getting.
C2H2.
Okay. C2H2. Acetylene. Huh? Ethyne, whatever. So So this molecule has D infinity H point group. What about C infinity V?
HCN.
Getting
HCN.
right. Any molecule, HCl, carbon monoxide. Why not? What not? And three. If you want to see, O, C, yes, like this. So again, C infinity V, it has what? It has C infinity and infinite times of sigma V plane. Only this much. It doesn't have sigma H, but it will have sigma V plane. Yeah, it doesn't have symmetry. I mean, this condition is not satisfied. C2 converted to C infinity is not there in these cases. So it just given as C infinity V. Okay, so with this, these are all point groups, and there are other 3 points. There are something called special point groups, called as mostly molecules have special point groups. One is tetrahedral, second is octahedral, which you are very much familiar with. Tetrahedral is TD, right? We generally give a symbol TD for tetrahedral. Octahedral, this I don't have to tell you, because all the inorganic complex, most of the complexes will have OH symmetry. It's octahedral. And then icosahedral. Have you heard about icosahedral? It's going to be a symbol IH. It's a special point group which has very high symmetry. For example, C60. One is C60 has icosahedral symmetry. Simplest one, if you want to see, if you have a minimum atoms to form icosahedral is 12 atoms. So 12 atoms, for example, I can say aluminum 12 cluster, Al 12 cluster, or titanium 13 cluster can have icosahedral symmetry. So what happened? I was standing in the same place for a long time. So this is tetrahedral, octahedral, icosahedral I can draw. Just basically 2 inverted triangles. Okay. So if you see, there will be 12 vertices in this. Oh. So you have to see the all the connected points will have atoms. Consider this icosahedral minimum point is say 12 atoms. 12 vertices you can say. So 12 atoms it needs. Examples are Al12. Okay, so this is aluminum cluster, and if you put another atom in between, so that can connect to all the points. So everywhere it can connect. All 12 centers to connect. So then that is called as this atom. So the example is Ta30 or platinum 30. So these are people you might have studied what is called as nanoclusters. So, small size clusters. So Ta30, which has a central icosahedral atom. Aluminum 12 doesn't have the central atom, but the structure could be icosahedral symmetry. And Ta13 is this one. Platinum also is possible. PT13 is possible. So these clusters are known. It's not really known. Gold is also known. Gold 13 is known. So these are nanoclusters which have very high symmetry. So that symmetry is found to be icosahedral. Okay. So this is you can refer it. It has huge symmetry elements. I can write it just for your record. I can write it how symmetry it is. The molecule is so E equals C5. C2, I is there, and then 15 sigma is there. So like this, you'll have so many symmetry elements present in icosahedral symmetry. This is IH. Okay. These are high symmetry groups. It's called as special group. Okay. Just for information, I'm just saying. So this is highly symmetric molecule. Icosahedral. So let's go to the systematic way of finding out the point group. Okay. No, I leave it. I'll come to the systematic way maybe next class. I'll introduce what is called as multiplication table, group multiplication table. Have you heard about this term, group multiplication table? Yeah, anybody? Those who are awake, can you tell what is group multiplication table? Let's try it for C2V, the symmetry elements. C2V, the example is water. So I give access for that. This is X, Y, Z. Okay, and then I define its symmetry elements. So water has C2V. That means it has E, C2. C2 we say Z axis, and sigma V plane, which is say cutting the molecule into half. So that is sigma V, or I would say maybe on the plane, that is XZ plane, and that is another sigma V on YZ plane. We call it as prime. Okay, I think with the labeling, I'm just giving which axis what it is. X, Y, Z. So in 3 directions you have X, Y, Z. But water is a planar molecule, 3 atom system, so it should be planar. So E symmetry has C2 in Z axis. So molecule is axis passing through this oxygen. Okay, I'm just calling that as Z axis. And I have 2 planes, sigma V and sigma V prime. And sigma V is which is I place it over this water molecule. So that is sigma V plane on XZ axis. And then there is another plane, sigma V prime, which I place it over Y and Z. So Y is coming out of the board, so I just place it here. Okay, so group multiplication table means you write all the symmetry elements present. So E, C2, Z, sigma V, which is the first one. Sigma V is Z. And then that is sigma V prime Y Z. Okay. And again in this column wise also write it. I have. So multiplication table. So basically if you perform 2 operations, so what is the outcome? That you have to fill it in this table. Okay, so obviously, if you perform C2 followed by sigma V, what is the outcome? That we are right. Say, let's start with you take the identity element and then multiply with identity. We are going to get the same because E you are not doing anything. Again E you are not going to do anything. So it's again the result is E. Whereas if you perform E and C2, it will result in C2 E. Again, this will become E multiplied by sigma V is going to same. The molecule is going to remain as such. Again, with sigma V prime, it is going to be remaining same. So always first row and first column is going to be the same. So it is C2Z in any molecule. So this is the XZ. Okay, so this is first row and first column we have finished. What about the diagonal elements? So this is 4 by 4 dimension, right? So what about C2 product C2?
Identity.
Can you please repeat it? I didn't get it.
Identity.
Ashok, you said E.
Yes.
Correct? Same thing, you do it with sigma V multiplied by sigma V. So basically you perform one sigma V, place the mirror on this sigma V, and you place one more mirror on that. So molecule is not going to change. So it's going to be E1. And again, sigma V prime multiplied by sigma V prime. To multiply it, so obviously what I'm trying to do is sigma V prime on water molecule. This is what I'm trying to do. So 2 times sigma V prime to perform. Basically, you're cutting the molecule into half. So this H comes to here, this H goes to here. I can write it here. So this is say H2, this is H1. Okay. So if you perform sigma V prime, what happens? You're cutting the molecule, so this becomes H1 comes here, this is H2 comes here. So 2 hydrogens are interchanged. If you perform another sigma V prime, you place a mirror on top of this position. So what happens again? This will be interchanged. So this is H2, this is H1. Right? So it was. So you came back to the starting structure. So basically, E prime, sigma V prime is again E. Okay, diagonal elements also easier. You have done it. What about these two elements? What do you do? C2 multiplied by sigma V. What you will get?
YZ.
Sigma V prime.
Sigma V prime. Prime is YZ. And then you please work it out how we are getting it. Okay. So basically, you have to multiply with sigma V multiplied with C2, or you can perform C2 first. So if you perform C2, again gets rotated, you get H interchanged, and then if you perform sigma V on XZ, so you get XZ is on the plane. Okay, so this remain as H1, this remain as H2. So it just remains. So this structure is obtained when we perform sigma V prime. That's why we got it. Sigma V prime. Now in this row, if you see, all the elements are different. All the symmetry elements are different. E, C2, sigma V, sigma V prime. So it should be unique. Okay, each row should be unique. So here C2, E, sigma V prime is there. So last entry has to be sigma V. You can work it out. You just check it. Whether my multiplying sigma V prime and C2 results in sigma V symmetry element. And what about the third row? So C2 into sigma V.
Sigma V prime.
Sigma V prime. This is YZ axis. And then what is not there is C2. In this row. Okay. And the last row. So C2 multiplied by sigma V prime. It will result in
Sigma V.
Sigma V you get. Because if you see column wise also, it should be unique. The entry should not be repeating. So the sigma b of xz, and what is left here is C2 of z. Okay, I think we have entered all the entries in this table. So this table is called as group multiplication table. It is very useful when you develop your character table. We develop what is called as a character table for each point group. So this will become very handy. So you please work it out. Those who are not very familiar on this, you practice with C2V, the simplest one. Once you are done with C2V, you perform for C3. Okay, the group multiplication table for C3. So C3V is ammonia example, right? So H. Or I think yesterday there was a news about a molecule detected in Venus clouds. Have you seen the news? It was there in every major news.
Yes, sir.
Phosphine.
Yes, sir. Phosphine clouds.
Yeah. So I think there are signatures of phosphine detected in Venus atmosphere. Whereas in Earth, the phosphine is a very dangerous gas, notorious gas.
Not present naturally, sir.
Whereas in Venus, it has been detected. So phosphine also has a C3V point group. Okay, so people are saying since phosphine is there, it could be either life form should exist when phosphine is there, because only life forms either by decomposing or by some way it can form in Venus. So people are excited about presence of phosphine in Venus clouds. So let's come back to the topic. So this phosphine or ammonia has C3V point group. You develop the group multiplication table for C3V. Okay. Say yes. Some of you can unmute and say yes.
Okay, sir.
Yes, sir.
See, it's weird to see a computer on your monitor, which I could not see anybody, but still we have to do this. Okay, fine. Tomorrow, maybe next class on Friday, I think we'll start with. I think I left one part that is called as the point group. What do you call the systematic identification of point group for a given molecule. Okay, there is a flow chart for a given molecule. How to arrive at a point group? We just see that. Then we take over. We'll just go ahead with multiplication table, and then we introduce what is called as groups, subgroups, like that. Okay. Finally, we'll develop what is called as a character table, which will become very handy when you interpret the spectrum. Yeah, IR spectrum or IR active, Raman active, or microwave active. So the ultimate aim is to find out whether the transition is IR active or not, or Raman active or not, or microwave active or not. Okay, so for that, this group theory through its character table will be very useful. So, any questions? Okay, already some people left. Okay, fine, carry on. As I said,
Excuse me, sir.
Yeah.
So I have a question about the elective course.
Elective course, yes, yeah. So I'll just save this. We'll discuss maybe, yeah. Because recording, I'll stop the recording. Otherwise, you have to download huge memory.